Welcome to the deep dive. Today we're tackling something really fundamental in particle physics.
We are. It's the difference between fermions and bosons.
Right. And our mission really is to unpack what sets them apart and, well, why you should care why it matters for how the universe works.
Definitely. We can start with what they do, their basic roles. Fermions. Think of them as the stuff, the building blocks.
Like electrons, protons, neutrons, the things that make up, well, everything we see.
Exactly. All the matter around you. Bosons, on the other hand, they're more like the messengers. They carry the fundamental forces.
Okay, messengers, like photons for electromagnetism.
Precisely. Photons, gluons for the strong force, the W and Z for the weak force. Oh, and the Higgs boson, too. That's the one giving particles mass.
Got it. So building blocks versus messengers. But beyond those roles, what's the deep difference? What makes them behave so, differently?
Okay. That really comes down to a core quantum property. It's called spin.
Spin. Now, are they actually spinning around?
No, not literally spinning like a top. It's more of an intrinsic angular momentum, a fundamental quantum number.
Okay, a quantum number. And the difference is in the value of this number.
Exactly that. Fermions have what we call half-integer spin. So values like 1/2 or 3/2, always a fraction. Whereas bosons, they have integer spin, 0, 1, 2, whole numbers.
It sounds like such a small detail, a fraction versus a whole number, but you're saying this has huge consequences. It changes their whole social life?
Immense consequences. It completely dictates how they behave in groups. For fermions, that half-integer spin leads straight to something called the Pauli exclusion principle.
Ah, Pauli. I remember that from chemistry.
You would. It's fundamental.
Yeah.
Pauli's principle basically says no two identical fermions can be in the exact same quantum state at the same time. They need their own quantum personal space.
Personal space. So that's why electrons in an atom don't all just pile into the lowest energy level.
Precisely. It forces them into distinct shells, different energy levels. It's what gives atoms structure, makes the periodic table possible, enables chemistry. Really, all the complexity of matter relies on this. Fermions are, you could say, quantum individualists.
Fascinating. Quantum individualists. So if fermions need their space, what about bosons? With their integer spin, do they follow the same rule?
Not at all. They completely ignore Pauli. They follow a different set of rules called Bose-Einstein statistics. And these rules say, well, I actually prefer to be together.
They like being together, so the opposite of fermions.
Completely the opposite. The more identical bosons you have in a particular state, the higher the probability that another one will jump in and join them. They're gregarious, you might say.
Gregarious particles. Okay, so this tendency to clump together, that must lead to some interesting effects, like lasers. Aren't they just tons of photons acting as one?
That's a perfect example. Billions of photons, which are bosons, all in the exact same quantum state, perfectly coherent. That's the laser beam. And this preference for togetherness also leads to something even more spectacular. Bose-Einstein condensation, or BEC.
BEC, I've heard of that. Super cold temperatures, right?
Incredibly cold,
Yeah.
near absolute zero. Under those conditions, huge numbers of bosons can all fall into the very same lowest energy quantum state. They become indistinguishable. They act like one single giant superparticle.
Wow, a superparticle. Something fermions, with their need for personal space, could never do on their own.
Not directly, no.
Ah, but you said not directly. Is there a loophole? Can fermions find a way around their own rules?
Yeah, in a way, yes.
Oh.
They could be quite clever about it. Under the right conditions, again, usually very low temperatures, two fermions can pair up.
Pair up, like hold hands.
Metaphorically, yes. For instance, two electrons, which are normally individualist fermions, can form something called a Cooper pair.
Okay, a Cooper pair. Two fermions together. And what happens to their combined spin? Does the pair as a whole unit
Behave differently.
Yes.
Yes. That's the amazing part. The Cooper pair, made of two half-integer spin fermions, actually has a combined spin that is an integer.
An integer, so the pair acts like a boson.
Exactly. The pair itself behaves like a boson. And that means these pairs can participate in those collective gregarious phenomena that were forbidden to the individual fermions.
That's incredible. So the fermions team up, become boson-like, and suddenly they can do things like
superconductivity. That's the mechanism behind it. These Cooper pairs can flow through a material as an electrical current with zero resistance. Absolutely none.
zero resistance. Wow.
And it's also the basis for superfluidity, where certain fluids can flow without any viscosity, any internal friction at all. It's fermions finding a cooperative way to exhibit boson behavior.
So let's sort of recap. It seems like we have these two fundamental families.
Right. Fermions making up matter, bosons carrying forces, different spins, fractional versus whole numbers.
Leading to totally opposite social rules. Pauli's exclusion for fermions needing space.
Versus Bose-Einstein statistics for bosons loving a crowd.
And that gives us stable structures from the fermions, but also these amazing collective effects like lasers and BECs from the bosons.
Don't forget the Cooper pairs.
Yeah.
The fermion teamwork.
Right. The incredible cheat, allowing things like superconductivity and superfluidity.
You've got it. This split, fermions and bosons, it's not just some neat category. It's baked into the quantum rules. It dictates how everything is built, how it interacts, from atoms staying stable to these really exotic states of matter.
So, thinking about it, what really stands out is this kind of cosmic balance, isn't it? You have the individualist fermions forming the stable structures we rely on, but they only exist and interact because they're constantly exchanging these very social, gregarious bosons.
It's a beautiful interplay. Two types of particles governed by opposite rules stemming from just that little property called spin, yet they work together to create, well, everything.
It really is profound when you think about it that way. Opposites attracting, or at least collaborating on a quantum scale to build reality, something to definitely mull over.